It's my great pleasure to be here. I have the unique status as being the most ignorant person in the room in terms of understanding actually these machine learning models. So I'm learning a lot today, which is great. I'm primarily an experimentalist, so I really I try to understand these things, and I'm trying to understand how we can use them to our advantage, but I have a long ways to go. But I'm going to tell you today about a project that we've been doing with my partner in crime, Samathi Raman, at ExxonMobil, with MIT and the University of Florida. So we're working with Yangsha Horn's group at MIT, and the graduate student who's primarily involved is Danielle Vivona, and then with Dave Hibbett's group at Florida, it's Hansel Montevallo. Okay, so what we're interested in is developing descriptors for metal oxides in the same way that many people have already developed descriptors for metal-based chemistry. And so in this situation, you have something like, okay, I want to do something like propane dehydro, and I want to be able to do it selectively in order to make propylene. And so I have some performance metric, which describes, say, like a total yield of propylene that I'm getting. And then what I want to, of course, do is have some kind of catalytic descriptor. And in fact, it's not likely that any single catalytic descriptor is going to be effective, that I am actually just going to have to be some sort of multiple descriptors in some kind of combination in order to actually lead me to anywhere useful. And this descriptor should be something that is an intrinsic property of the material, probably the surface of the material. Maybe it correlates with something in the bulk. That would be helpful if it did. And this descriptor should be something that we can easily calculate, that it's transferable across many, many systems. And then hopefully it would even be something that we could experimentally verify, because that would make me feel much better. The approach that we're gonna choose is going to be ultimately something more like this glass box type of approach, because I'm not capable of understanding these black box things and figuring out what's going on. So, and the problem of interest that I'm going to present very briefly today is it's a trivial example for like chemical looping using a metal oxide. Okay, so I'm passing some alkane over a material that's rich in oxygen. There's no oxygen being co-fed, and I'm just going to deplete the oxygen out of that material to a certain point. And the reaction that I'm hoping to perform is an oxidative dehydro reaction where I'm producing the alkene, and I'm going to remove basically the oxygen from the metal oxide as water. And then what I can do is I can circle that back around, and I can pump the oxygen back in. Okay. And we've been working on that some at ExxonMobil in a fundamental way with the team. So Pedro Serna was involved, Kun Wang, and Sophie Liu. Oops, wrong way. And so I need then to understand a couple of different things. I need to have a matching of rates of diffusion in the bulk metal oxide, and then I have to the surface reaction. And then the surface reaction, not only do I want to have a rate that's somewhat correlated to the diffusion reaction, but then it also, again, I hope that's a very selective reaction. And so I need to understand this interplay between transport and reactivity, which is sort of the title of my slide. Okay. All right, so if I look at the lifestyle of an individual particle, I'm going to start off with a case where I'm fully oxygenated, and then as I deplete, I could have a situation where, I deplete at the surface, and that I set up some kind of concentration gradient, which then drives the fusion of oxygen from the bulk to the surface. And ideally, I would be able to suck all the oxygen out of the particle, or to some degree, right? What I want to avoid happening is that I have some kind of phase transformation at the surface, which effectively cuts off that diffusion or strongly alters the reactivity. But this is some things that we have to at least consider as possibilities in our system. And so one of the things that we're going to eventually have to implement in all this is sort of what is the stability of these structures, and as you deplete oxygen, how they transform. Okay. Now, the descriptor sets that I'm interested in, I kind of have classified into three forms. So there are those that I would call structural descriptors, which are the geometry of the oxide of interest. And you can use MapMiner or these other programs to generate a lot of these types of descriptors. But I mean, we're looking at things like, if you just kind of distill it down, things like the size of the cations in the metal oxide, what are the windows that form, if I was thinking about passing an oxygen atom through, and what's the, the free volume of the lattice. And there are also things to do with specific coordination environments, say like the number of metal oxygen bonds. What's the coordination of a metal cation? What's the coordination of an oxygen? Then there's a category that I would call electronic descriptors, which describe the strength of the metal oxygen bonds. And you can relate this to other features of the electronic structure, things like the band gap, to charges on the cations, charges on the anions, exactly. And so, I mean, we're going to maybe naively assume that everything's, 2- on the oxygen, but you can actually look at the small changes around that, and that might tell you something about the bond strength. And then there are various other, and so the O2P band center, for example, is another commonly used descriptor now. And then there's a third category, and this is the reason why we decided to work with Yang, is that she had been looking at phonon modes in lithium-containing materials and looking at lithium ion hopping. And so I came to her and I said, well, could we do the same thing with like oxygen ion hopping in a metal oxide? And she said, not only could you do that, but she was already working on that. So we then decided to fund a project with her to work on that together. And, one could argue whether or not you need the entire phonon band center or whether you just want to pick out certain particular phonons. But at least to start with, let's just say we're just going to look at phonon bands. And so then I'm going to very naively construct some kind. So this is my glass box, Brian. I'm going to just say I'm going to have a very simple equation that's going to say that my barrier for oxygen transport through my metal oxide lattice is going to be some kind of principal components that maybe are each of these types of descriptors, maybe some structural descriptor, maybe some electronic descriptor, maybe some phonon-based descriptor, and I'm just going to combine them in a completely nonsense way, at least to start with, and then hopefully I can learn something about the physics that'll actually teach me what these functional forms ought to be. Okay? All right. Another thing that I should point out is that, at least for the structures, there are already many. There's something close to 40,000 structures in the inorganic crystal structure database of pristine oxides. One thing about that is it doesn't include dope systems, right? And in many, many cases, we're interested in actually doped oxides in order to actually induce transport. If you read papers where they have done things like they have calculated the diffusion, or not calculated, excuse me, measured the diffusion barrier of oxygen in a material, something like lanthanum alumate, if you actually read the paper, it's like, well, actually they put in a little bit of fairy dust in order to generate the vacancies, in order to actually be able to measure a transport rate. Because otherwise, if you have something where you have two irreducible cations like lanthanum alumate, the graduate student would spend their entire career making one measurement. So to be a little bit careful then in sort of correlating experimental data then with what we're going to calculate. I mean, and depending upon the dopant concentrations, of course, we can explicitly include those. We have, say, cell sizes that are on the order of maybe 80 atoms or 160 atoms or something, then it's not so big of a problem. But if they are really present in very low amounts, that wouldn't be maybe very practical. And again, so Tim Mueller wrote a very nice paper classifying different types of oxides, then from the inorganic crystal structure database. He put them in something like 41 different classes. And then they again have a variety of oxygen and metal cation coordination environments. And so we were going to start with a couple of the most common ones, things like perovskites, RP materials, but eventually we'd like to get to things that are more exotic, that are less studied, because that's the whole point of this project, is to see if we're missing something that might be interesting outside of the sort of standard materials that have already been considered quite widely. Another thing that we can do is we can take advantage of the sheer number of calculations that have already been performed in this area. Perovskite calculations have been done quite a bit. Usually, if you access those databases, they don't have things like barriers for oxygen transport, but they have all the descriptors that we just talked about in terms of electronic structure, right? So they have things like O2P band centers. I can just download those for a huge number of structures. And they even have ones for phonon bands. So hopefully then I'm not going to have to recalculate everything myself. Once I establish what my sort of descriptor equation is, if you will, what the model is, then I will be able to just do a few calculations, and I will be able to hopefully make predictions on a very large range of oxide materials. At least that was the naive dream that I had when we were developing this project. So In terms of its actual execution, it goes like this. We were using materials atomistic simulation toolkit, which comes from Wisconsin, Dane Morgan's lab, and Sumathi implemented this on our computers and also at MIT. And then this allows for at least some job automation in terms of I give it a structure, it automatically sets up all the daughter jobs for calculating the vacancies that form and the transition states for the barriers. And then I can extract then those barriers. And so what I'm doing then is I'm going to calculate some barriers on a basis where I don't have that data available to me. And then I'm going to use these set of initial calculations of hopefully something on the order of about 1,000 barriers, maybe a little less. And then I'm going to be able to make predictions on other things. But there are a few complications in this process. There are different considerations around actually when you make a vacancy. Do I take that vacancy out as basically an O atom? Or do I take that out as O2 minus? And that actually is an important consideration of whether you believe it's an intrinsic or extrinsic vacancy that you've created. And in addition, again, we have this dopant issue that we would, if you really want to look at non-stoichiometric types of situations, that really opens up the space quite a bit. Another thing that we did do is we did a few ab initio MD simulations in order to verify that you can actually, the barrier that you extract actually matches a barrier that you would get just from looking at the pathway as I move an oxygen through the lattice of the material. So that was comforting that I essentially get something that matches pretty well between my MD simulation and the DFT calculation that's sort of naively predicting what the pathway should be. So that means that there's not like, at least under the levels of oxygen depletion that we looked at, there aren't large levels of concerted motion or something like that that one needs to consider. And then another thing that we can do is that in order to generate sort of the descriptors in cases where we don't have it, is that we can use something like this crystal graph convolution neural network that was developed by Jeff Eastman at MIT. And Jeff Grossman at MIT, excuse me. And we use that in order to take then these large number of calculations that I described from the materials project. And then Jackie then performed a fit based upon the learning from the CGCNA. And similarly, there's again a database of phonons band centers, and we can do the same thing in that way. And then you can use then those predictions in order to allow you to get some kind of confidence that, again, I don't have to calculate every single oxide. Maybe I can already make some kind of prediction in cases where I'm missing data. Okay. And then this is a pathetically small training set that we used to start. Again, now we've actually gotten further along than this, but okay, this was a very, very small data set. And, using those numbers from the CGCNN and the calculated barriers that we have, and are in cases where we don't actually explicitly calculate the phonon band modes or the O2P band centers. I think all O2P band centers we pretty much did actually have explicit calculation. We can predict the migration barrier with a reasonable accuracy. And the great news is we don't have to be that accurate. So what is my accuracy goal here? So my accuracy goal, something on the order of like 0.2 EV, that's pretty good. So what I can do is, if I have 50,000 oxides and I want to narrow down to some subset of oxides that I want to actually test for oxygen transport, and let's say I want a range that the barriers need to be in the range of say 1.1 to 1.3 EV, well, now this generates that set. I don't have to be super accurate in this particular case on the diffusion side. And so then I can look at that subset. I can eliminate large numbers of compounds from that subset because of their cost or they're difficult to synthesize or whatever. And now I have a group that I can actually start to play with experimentally. When you're moving from the bulk to the surface, things are a lot nastier. So now I still have all my problems that I had before in terms of how do I consistently treat all these oxides, which may have very different magnetic structures. but now I have an additional huge problem in choosing surface terminations. So in many cases, I have limited characterization about what surfaces are actually present. And it's known that surfaces, just like in metal cases, as metal surface science studies have shown, metal oxides also reconstruct. So just using bulk terminations, is that going to be sufficient? Well, I don't know. And the other thing that at least for me personally, is that my human imagination is not nearly good enough in order to postulate what all the possible descriptors could be for now for reactivity. For ion migration, I had a pretty good set already. And people have been working in the field long enough that things were known. Now, when I go to descriptors for oxygen surface reactivity, I've got something like O2 p-band center, and that's about it from the intrinsic properties of the metals. And there's probably other kinds of structural descriptors in terms of distances at surfaces and things like that, and level above the surface that things are sticking out. I could start to work on that, but it's not so simple. And so, what we're trying to do again is trying to get some kind of descriptor for the transition state based upon something simple. I mean, this is an example that comes from Prashant Vishlar and Enrique, that dates back almost 8 years now, where they're looking at HPAs, and they were looking at that because those structures are all fairly identical, right? And they're just substituting in one atom or the other. One thing that I'm extremely concerned about is if I move from one class of oxide structures, which is where we have started also with a particular set of oxides, and move that to another class of oxide structures, that my transferability will be poor. And then my biggest problem, even beyond that, is DFT really good enough to adequately describe the selectivity? So that I think that's like almost a killer for us, is that, and essentially, if we're talking about a very good ODH catalyst, now we're talking like in the 90s for selectivity. A bad ODH catalyst is like in the 70s for selectivity. That difference in terms of what that means for a delta G, not big enough probably to do this, at least for this particular reaction, because you are relying upon a mechanism where the strength of the CH bond is going to be ultimately a lot of the determining factor in terms of the activity. And so then the selectivity is just sort of a wash underneath that, which has to do a little bit with maybe like interaction of the radical state with the radical state that's formed on the surface. Okay, I'm going to skip this part, what we actually did there. To close then on some other areas of interest. So we at ExxonMobil, we use machine learning and AI for many things. Not related to catalysis. So for example, we have the traveling salesman problem, right? So we're trying to organize the delivery of oil tankers all around the world to refineries. We also use it in a program that is called Transparent Earth. I love that name. It's basically the idea is that we're using seismic data in order to look into the earth to find out where the gas and oil deposits are. AI has been incredibly successful in that arena. Not as successful, at least to date, in the arena that we're playing in today. So we thought that we had a ton of historical data that we could mine that would tell us all about some new great catalysts that we had missed in the past. And the problem that you might not be surprised to learn is that we collected a lot of data at the same conditions for the same catalysts over and over and over again, very narrow ranges. And so interpolation, not a problem within those narrow ranges. Extrapolation to new systems, not so good. We have been playing around a little bit with machine learning potentials for dynamics, as Boris was describing this morning. That kind of thing is of high interest to us to understand if we have a bimetallic, how does it segregate? Does it stay together? Under what kind of oxidation reduction conditions? So because all these pre-treatment conditions, as Mark was talking about, the synthesis conditions are incredibly important to the final structure of your catalyst. And so, we would like to be able to understand the dynamics of those systems and how the catalyst is built. Another paper that we're of high interest, we tried to hire Daniel. I think he's here in the audience somewhere. He's looking at machine learning to find new SDAs for zeolites. That's another area of high interest for us, right? Is if we currently have a zeolite that we have a very expensive SDA for, a structural directing agent, these organic molecules that actually are how you build these metastable zeolite structures, then we were looking for replacements. It's a very complex problem. The unit cell matching between the SDAs and the unit cell of the zeolite are not a one-to-one match. Sometimes you have to go to very expansive systems. in order to see how the molecules arrange and consider all the different configurations and so forth. And then finally, you can use these applications for looking at, again, Mark mentioned about CO2 absorbance, flow battery molecules. There are other areas of interest that we're involved with, but they have not been successful to date as transparent Earth. So anyways, with that, I'll close, and I'd be happy to answer maybe one or two quick questions. I'm sorry if I went off. Yeah, so.
Thank you, Randall. Very interesting talk. I have a quick question. So you probably mentioned it, but I didn't notice. Why do you assume that the descriptors are not coupled? Why do you assume that they are all independent?
Oh, that's just like the naive beginning. There's no way you should assume it. But we can see what's correlated, right? If you actually have things, you can see which.
But if you find one at a time, you don't know if they correlate, right? But you seem like you're looking for one at a time, right?
No. We put them in all at once.
Oh, but they are not coupled. So
no, not coupled.
All right. Randy, nice talk. Seems fun too, like a lot of our research. Quick question. I want to know if you're interested in eventually using those descriptors to help you with synthesis, tying the levers of synthesis back to those descriptors.
That's something that, when I first heard Mark's talk, I think it's a very interesting idea. We haven't really gotten anywhere in that space, but I think it's certainly an interesting prospect to think about. Yeah.
I'm curious if you, rather than pre-defining the descriptors, have you tried to use ML to identify descriptors?
So I don't know how to do that. Somebody needs to teach me how to do that. How it would search for something that I can't define. But I mean, because of my background, I really like this sort of more like glass box approach where it's things that I can understand, where I can name, as opposed to a principal component, which is some nebulous thing. So I don't know. I mean, I would like to be able to say to people, the reason why this material works is exactly because of this feature, right?
Yeah,
this
totally.
bond, this energy, this charge.
Agreed, but I just wonder if we're limiting ourselves by things that we might intuit, and there could be a possibility that this comes
Sure,
in.
absolutely.
Yeah, last question first. So, very nice talk. You touched on a very important point about the accuracy of DFT. So if you have a very good catalyst and a mediocre catalyst, and that could be some small changes in activation energy,
Yes.
or energy, quickly that number of accuracy that one needs.
I mean,
it would be nice to quantify.
so if you quantify what effectively the Intiomanner excess, right? And we need, if you want high selectivity, that's one way of looking at it, is think about it as like a chiral reaction, right? So I think those numbers are on the order of less than 1/10 of an EV, right? They're like 0.05 to 0.1, somewhere in that range is what you need. It depends on the system, of course, but that's the number that I can vaguely remember that I calculated once upon a time.